Abundant life. It's the hallmark of our planet. But it's water that makes us unique.
Liquid water is the essential environmental requirement for life on Earth. So when we look for life elsewhere, we start first by looking for liquid water.
Our search has taken us to an alien world that seems to defy the laws of physics. A place where water can't exist, but shows us evidence that it might.
We have what we in science call an anomaly.
NASA's Phoenix lander will find out if life is possible on this desert planet. Welcome to Mars, the water world.
Load relief kit crate is in, vehicles responding. Vehicles recovering very nicely from the liftoff transients.
August 4th, 2007 at 5:26 a.m. This Delta II rocket blasts off from Cape Canaveral. In its nose cone is NASA's first robotic Mars scout, the Phoenix lander.
At this point, we have a strong signal from Phoenix via Odyssey.
At NASA's Jet Propulsion Laboratory in Pasadena, California, engineers monitor the progress of the $500 million mission.
All stations, we have confirmed crew stage separation and UHF signal acquisition via Odyssey. Atmospheric entry on my mark. 3, 2, 1, mark.
The new generation lander enters the final phase of its 400 million-mile journey to Mars.
1 minute since LOS, standing by for signal reacquisition.
Phoenix will search the Arctic plains of Mars for the building blocks of life, including carbon, nitrogen, and most importantly, water.
Touchdown detected. Landing sequence initiated.
Phoenix intends to prove that life on Mars is, or was, possible. If it does, then life on Earth is not unique. This is a test simulation, but on May 25th, 2008, the team at JPL attempts this for real.
Primary objective of Phoenix is to explore the Martian Arctic and to determine whether or not conditions for life are there today or existed in the past.
If Phoenix finds what it's looking for, it will change our understanding of the solar system. If there's life on another world, it could mean that the universe is teeming with it, that the aliens of our science fiction could be a reality. Phoenix might even find them. But finding the signs of life on a planet millions of miles from home is an incredibly difficult challenge. The lander hasn't been designed to find life directly. It's been built to find the necessary ingredient for it: water. Chris McKay is a planetary scientist at NASA's Ames Research Center.
When we look at life on Earth, we see an enormous diversity. Organisms that do all sorts of different chemistry, live in all sorts of different environments. But the one thing that all organisms on Earth have in common is a requirement for liquid water. So naturally, when we look for life elsewhere, we start first by looking for environments that had liquid water.
Here on Earth, wherever there's water, there's life. Even in temperatures as extreme as 14 degrees Fahrenheit, organisms can survive. So if we find signs of water on Mars, we might find life too. But why are we looking on Mars? Professor of Geomorphology Vic Baker explains.
30 years ago, a spacecraft called Mariner 9 produced about 9,000 pictures, many of which showed large channels and valleys. And it was very obvious that these channels and valleys are directly analogous to what we see on the Earth, formed by water.
Scientists are stumped by these images. It definitely looks like water erosion, but as far as they know, there is no water on Mars. Its atmosphere is too thin to support it. The air pressure on Mars is less than 1/100th of the Earth's, which means the air on Mars's surface is the same as it is here on Earth at 110,000 feet above sea level. That's 20 miles high, nearly 4 times the height of Mount Everest. Scott Rafkin is a planetary atmosphere specialist at the Southwest Research Institute in Boulder, Colorado.
It's fairly common knowledge that if one goes camping or hiking and you go up to higher altitudes and you go to boil your water, as you go higher up, it boils at lower and lower temperatures. That change in altitude is what you're really doing is changing pressure. As you go up in altitude, the pressure is becoming less and less. And so what happens is that as you go higher up, it becomes easier to boil water. You don't need to raise its temperature as much.
This experiment shows the effects of Mars's atmospheric conditions on water. Gradually removing air from the chamber reduces the pressure. At first, nothing happens. But when the pressure drops to the equivalent of Mars's atmosphere, the water boils. Water normally boils at 212 degrees Fahrenheit, but at this low pressure, it boils at room temperature. On Mars, this happens at just 50 degrees.
The stability of water on any planet is tied to primarily the pressure. And the pressure on Mars is so low that if one could have liquid water sitting out on the surface, it would simply boil.
Mars's ultra-thin atmosphere creates another problem for water to exist here. There's not enough of it surrounding the planet to insulate it. Mars is ice cold. At its warmest, it's just 70 degrees Fahrenheit. At its coldest, the temperature drops to -225.
Now, of course, on Mars, we have another problem, which is that it's very, very, very cold. So even if one had the higher pressure so that the water wouldn't boil off, it would just freeze solid, like a rock.
The existence of these channels and valleys that appear water-carved baffles scientists.
The question is, how do you have these two things? How do you have a planet that is cold and dry with a thin atmosphere, and yet clearly, in its past, had flowing water?
Over the years, scientists have offered many theories to explain the features seen on Mars's surface.
People have suggested, well, maybe it's carbon dioxide liquid, or maybe it's lava, or maybe it's wind. Well, wind, lava, carbon dioxide could have formed many of the features we see on Mars, but they can't explain all the features.
And for the past 30 years, this has been the major source of science controversy. And it's the reason that the current NASA program is sort of directed with this euphemism, follow the water.
Using the latest science provided by Phoenix, NASA hopes to prove once and for all that they were made by liquid water, a substance that shouldn't exist on the planet. But the debate is growing more controversial. In June 2000, scientists got very excited about these images taken by the Mars Orbiter camera, a probe that has been circling the red planet since 1997. This one was taken in 1999, and this is of the same location in 2000. The images clearly reveal a changing landscape. To geologists like Vic Baker, these recently formed features look strangely familiar.
On Earth, we would call them gullies. They're sort of on the scale of hundreds of meters, no more than a kilometer. They're patterns like the veins in a leaf or branches in a tree that result from how water falling on the surface organizes itself into larger and larger drainages.
These gullies and alcoves seem to have been recently formed by water. They have appeared in the southern hemisphere of the planet, on slopes that get the least amount of sunlight during each day, one of the coldest parts of Mars. Their similarities to gullies formed by water here on Earth defy logic and the laws of physics. So what created them? Did water flow across Mars in its past? And is it still flowing today? On May 25th, the Phoenix lander, NASA's $420 million mission to Mars, touches down on the red planet to answer two questions that have vexed scientists for decades. Is there water, and could there be life? At the heart of this debate lies this rock that landed on Earth from Mars. Discovered in 1984 in the Antarctic, it's 6 inches long and weighs over 4 pounds. It's called the Allen Hills meteorite, and it's one of just 34 Martian rocks that have been found here on Earth. Johnson Space Center astrobiologist Dr. David McKay has studied this meteorite for more than 10 years.
Allen Hills is unique among the Mars meteorites because it's so old. It is by far the oldest of the known Mars meteorites. And furthermore, with an age of 4.5 billion, it is older than any rock ever found on the Earth.
McKay believes it contains proof life was possible on Mars. Using high-resolution scanning electron microscopes, he examines the meteorite and discovers tiny globules of iron and magnesium carbonate. Elements almost certainly formed and deposited by liquid water.
Carbonates are significant because they show that not only was water there, but it was relatively low temperature.
McKay is convinced that this proves Mars's atmosphere was once very different and could sustain flowing water, so the conditions for life were present. By radioisotope dating the carbonate globules, McKay comes up with a figure. Water flowed on Mars 3.9 billion years ago. NASA's current crop of rovers scouring the planet backs up McKay's findings. This is Meridiani Planum, the landing site of the rover Opportunity in January 2004. It's a dusty area the size of Oklahoma. Photographs relayed back to Earth reveal the soil is littered with countless BB-sized rocks. NASA scientists nickname these puzzling objects blueberries. On Earth, similar deposits form, but only in standing water or hot springs. Geologists have uncovered blueberry-like clusters dating back millions of years in Lake Superior and near the hot springs of Yellowstone National Park. Their discovery on the vast plain of Meridiani Planum suggests this area was once saturated with water, or was even an ancient lake. In fact, closer examination of the surface of the planet reveals that much of it was once a water world. These images, taken by a high-resolution stereo camera aboard the Mars Express spacecraft, reveal Mars's watery, almost Earth-like past. This is a large depression called Ioni Chaos, and next to it an outflow channel called Aris Vallis. They're the remains of Martian river systems, and to planetary geologists like Jim Rice, clear evidence of ancient catastrophic floods.
We took every river on Earth and put it in one spot, had them flowing at the same time. Some of these flood channels on Mars, when they were in full force, are 20 or 30 times bigger than those.
What was it that happened in the Martian past? Why do we have a planet today that is very cold and dry and gives every indication that we don't have liquid operating on its surface? Why in the past did we form these channels?
If Phoenix can figure out if water flowed across the surface of Mars in the past, it will explain the valleys and canyons we see today, and take us one step closer to discovering if water still exists, and even life. Now the Phoenix mission can confirm what the experts suspect.
It must have been warmer, at least for some period of time, so that we could have liquid water on the surface. And the pressure must have been higher than it is now, or the water would have boiled away.
Early in its evolution, Mars was much warmer. In fact, it was boiling. $4.6 billion years ago, our sun bursts into life and our solar system forms around it. Both Earth and Mars are huge balls of lava, boiling at over 12,000 degrees. Slowly, they begin to cool. Dr. Peter Smith heads up the Phoenix mission from its base at the University of Arizona.
Earth and Mars formed at about the same time, but Mars is only half the diameter of the Earth, and therefore it would cool more rapidly.
Mars's size proves to be the crucial factor in its transition from a fiery molten ball into a warm and wet planet. In this demonstration, two globes are used to represent Mars and our own planet, Earth. These scale models exactly replicate the difference in size of the two planets. Mars, shown here on the left, has half the diameter of Earth. Both spheres have been heated to the same temperature. Now they are cooling naturally. Infrared time-lapse clearly shows how quickly the smaller sphere representing Mars cools. Mars was cool enough for water at a time when Earth was still a red-hot ball. This water comes from comets. The early solar system is littered with large asteroids and comets made up of ice. As they crash into the planets, the ice melts. On superhot Earth, the water boils away instantly. But Mars is cool enough to hold on to the huge quantities of water released by impacts.
And in that cooling, liquid water would be stable on the surface long before it would be stable on the Earth. And so during that period, it may be that you had rains and valley systems and lakes and all kinds of Earth-like situations.
Scientists believe that 3.9 billion years ago, Mars had the climate and atmospheric conditions to support liquid water, an essential ingredient for life.
Now, in the early days of the history of our solar system, this planet, the Earth, was not a good place for life to develop. We had noxious gases all over the places, volcanoes belching out all sorts of stuff. Mars was warm and wet and wonderful. It was the most likely place for life to develop.
Today, Mars is no longer warm, but is it wet? Understanding what happened to Mars's water is the primary goal of the Phoenix mission. Its success might hold the key to answering a 30-year-old question. Does water still exist on Mars? Scientists are now certain that Mars was once warm and wet. Pictures of ancient riverbeds, blueberries on the surface, and carbonate globules inside the Allen Hills meteorite confirm this view. But if there was water billions of years ago, where is it today? The question of whether water still exists on Mars will only be settled when NASA physically finds it. And that's the job of the Phoenix lander. It's being sent further north than any previous mission, to a site chosen because frozen water might sit below the surface. In 2003, NASA's Odyssey orbiter produces this image. Using its gamma-ray spectrometer, the spacecraft maps levels of hydrogen in the upper 3 feet of Mars's surface. Since high levels of hydrogen indicate the presence of frozen water, scientists think that these blue and violet areas, the densest concentration of the element, reveal an enormous frozen reservoir.
In fact, there's so much water in the polar areas and the nearby ice terrains that if you spread that water around the surface of Mars, that alone would inundate the surface of Mars on the order of 6, maybe 10 meters deep.
Phoenix's first job is to confirm that the hydrogen-rich area is in fact made up of water. Then scientists can begin to piece together the chain of events that lock the water under the planet's surface. Maybe then they'll begin to understand how the recent wet spots appeared. Some scientists believe they are a remnant of ancient climate change. Mars cools much more quickly than Earth, allowing water to exist on its surface. But a drastic shift in atmospheric conditions means it can't hold on to it. Earth's large molten core generates a magnetic field which protects our atmosphere from solar radiation. But Mars's small core cools so much that it no longer produces an effective shield. Solar wind blasts away its atmosphere and most of its water. Pressure falls and the temperature plummets. Whatever water it has boils away or freezes solid, leaving the Mars we see today, a frozen world. Up until recently, scientists believed that Mars's core is so cold that it is no longer able to crack and move the planet's surface.
The Earth releases a lot of its heat continuously by a process that's known as plate tectonics, where the continental masses of the planet are actually shifted by the formation of new crust in the ocean basins. Mars doesn't have that.
But the discovery of the gully features, the wet spots, suggests that Mars's core hasn't cooled as much as they thought.
Because it can't release its heat as efficiently as Earth, one idea is that this heat builds up with time, and episodically there's kind of a burst of heat release that will melt the ice in the Martian permafrost. And that water comes onto the surface, perhaps associated with gases that change the composition of the Martian atmosphere to a greenhouse kind of condition. And so you have a temporary, unstable state where Mars is warmer and has water on the surface.
These small flash floods could be the wet spots that dot the surface of the planet.
It's natural to suspect that maybe this volcanism that has happened in recent history and the water activity are somehow related. But this is one of the mysteries we're trying to investigate, and I think it's one of those that the Phoenix lander may be able to shed some light on.
By finding ice and analyzing its composition, the Phoenix lander is designed to map the planet's ice history It will tell us how geothermal activity and atmospheric change have affected Mars's ancient water.
Load relief kick rate is in. Vehicles responding. Vehicles recovering very nicely from the liftoff transient.
Phoenix's quest represents a journey into the unknown.
Up to now, all of our exploration of Mars has been superficial. We take pictures from orbit, we drive around on the surface, and maybe we dig down this deep, either by dragging it with the wheels or with a little arm or something. We maybe get down this far, and that's it.
But Phoenix is set to change this. It's designed to endure Mars's northern latitudes and to analyze subsurface ice. NASA hopes its findings will throw light on how water interacts with the geology of Mars, the key to unlocking the story of past atmospheric change. In order to achieve this goal, it's been built to do something no other Mars lander has done before.
Phoenix is going to arrive on Mars and land and dig.
A sophisticated robotic arm will dig down 3 feet into the frozen subsurface to where the layer of water is believed to be. At nearly 8 feet, the arm is the most important tool on the lander. It's designed to dig trenches, scrape ice, and deliver samples to other instruments on the lander's deck. No one knows the capability of this arm better than Phoenix's lead scientific investigator, Dr. Peter Smith.
The robotic arm in digging on the surface is doing something very difficult because it's being controlled from 100 million miles away. And so the interaction of using the arm and seeing through the eyes of a camera is not simple. It's like going out to drive a semi-truck with never having driven one before. The truck works, but learning how to shift 18 gears is not so easy.
If working properly, Phoenix's robotic arm will drop ice samples into a device called a Thermal and Evolved Gas Analyzer, or TEGA for short. TEGA has 8 tiny ovens, about the size of an ink cartridge in a ballpoint pen. Not unlike this one. Once a sample is successfully sealed in an oven, the temperature is slowly raised at a constant rate. As the temperature edges up to 1800 degrees Fahrenheit, the ice and other volatile materials in the sample vaporize into a stream of gases.
So if you think about what happens in your kitchen when you put, say, some sort of food in the oven and you start to heat it up, it's cooking nicely at 200, 300, 400 degrees. But if you start to crank that oven up 800, 900 degrees, 1,000 degrees, what's going to happen to the organic materials in there? Well, they're going to turn to smoke. They're going to come out, and like in my kitchen, they're going to set off the smoke alarm. And you're going to be doing an experiment just like TEGA.
Roasting the samples of soil and ice at 1800 degrees releases what are called evolved gases. A mass spectrometer will then scan these gases for minute quantities of hydrogen, oxygen, carbon, and nitrogen, the elements of life. But Phoenix's sophisticated instruments do have a limit. Each of its 8 ovens can be used only once. So as it digs down, it will take samples at 8 different depths. NASA hopes to then map the changing character of the ice. Scientists hope these precise measurements will reveal the evolution of water on the planet and possibly uncover the existence of life. To get a head start on the kind of data the lander might send back, the Phoenix scientists set out to replicate their experiments here on Earth. The geology of Mars and Earth is surprisingly similar. Mars is a cold, dry desert landscape of sand and rocks. But both planets share land features like volcanoes, canyons, and valleys. This is the most Mars-like place on Earth, the Antarctic.
Mars, when it was at its warmest and wettest, would have been like Earth at its coldest and driest. That's why, to me, going to the dry valleys of Antarctica is the next best thing to going to Mars.
Here, Chris McKay and Peter Smith are going to do on Earth what Phoenix will be doing on Mars.
The idea is to make the connection between what Phoenix will measure on Mars with what Phoenix would measure in the dry valleys of Antarctica.
They're digging down to ice to see if life, or the conditions for life, exists in this inhospitable terrain.
We go from a surface soil, which is kind of reddish and definitely of a different character than the lower soils, and we're going to measure layer by layer down to ice. We're using instruments on the deck of the spacecraft, and our robotic arm scoops up samples as it digs down and presents them to the science instruments, which analyze them right there on Mars. I think just by looking at these soils here, you can tell that liquid water's been at work. If we could see that on Mars, we have a place where we have a habitable zone and perhaps a place where life could live.
McKay and Smith's analysis of Antarctic ice reveals that life can exist in the sub-zero temperatures found on Mars.
It's really quite phenomenal what we can find in the dry valleys and in the high Arctic, how life can make do with small, transient amounts of liquid water.
These life forms are called extremophiles. They're microscopic bacteria that thrive in extreme environments. They were first discovered 40 years ago in the 160-degree hot springs of Yellowstone National Park. Since then, others have been found living deep under the ocean, in supersaline environments, even in the uranium-rich pools of water in nuclear power stations. But it's the ones that live in the sub-zero temperatures of Antarctic ice that interest the Phoenix team. They reason that if microbes can be found here, then why not on Mars? So if Phoenix finds ice, it might just find evidence of life locked inside it.
The other remarkable thing about polar deserts is how well ice and cold in general preserves evidence of life. We know that you can go up into permafrost in Siberia and dig out mammoths that have been frozen for 10,000 years or more. On Mars, we're hoping for the same effect. We're hoping to find, frozen in the ice on Mars, evidence of life that may have been preserved maybe for millions, but maybe even also for billions of years. Frozen micro-Martian mammoths, if you will.
Not only will Phoenix detect changes in atmosphere and temperature, it has the ability to identify organics, crucial to the search for life.
Our mission was designed specifically to touch water in the form of ice and to try and understand the properties of that ice, its history, its interaction with the soil, its interaction with the atmosphere, and really explore the question of is there or was there ever life on Mars?
By analyzing the soil samples, Phoenix might finally identify the building blocks of life: carbon, hydrogen, oxygen, and nitrogen on Mars.
And if we saw the organic materials, energy sources, and liquid water present in the past, we would say this is a habitable zone, and perhaps some sort of Martian life could live there.
With the Phoenix mission, NASA's 30-year search for water on Mars could finally come to an end. And by following the water, it might just find life. May 25th, 2008. NASA's Phoenix lander reaches the end of its 9-month-long journey to Mars. It now begins the hunt for life, or at least an environment that could have once supported life. But does NASA really think it can find this on the frozen wastelands of Mars? The answer is yes. This is because of an accidental discovery made by the rover Spirit.
Spirit's most significant scientific discovery came 1,200 days into its 90-day mission.
In 2007, a moving part on Spirit malfunctions. The failure leads to the best evidence yet that Mars was once capable of supporting life.
The right front wheel on Spirit doesn't turn anymore. It's failed. But the one good thing, the silver lining here, is that as we drive and we drag that wheel through the soil, we dig a trench. And every now and then, something interesting will pop up in the bottom of that trench.
X-ray analysis of a patch of soil churned up by the stuck wheel yields unexpected results. It is composed of about 90% pure silica.
That was just a complete unexpected discovery, pure serendipity, and frankly, if the right front wheel had been working properly, we might not have found it.
This $320 million breakdown reveals more evidence of water. On Earth, high levels of silica occur in only 2 places: hot springs or fumaroles. Both environments bubble with water and life.
The thing that's important about the silica discovery is that you can go to hot springs and you can go to fumaroles on Earth, and in both instances they're teeming with microbial life.
Spirit has discovered evidence of a habitable zone on Mars, a place where extremophiles like those on Earth could have thrived, and may even exist today. What's more, the idea of Martian life is backed up by the 4-billion-year-old Allen Hills meteorite. Structures inside it reveal what some believe is the first real evidence of Martian life forms. David McKay heads the team that made the discovery.
We discovered in Allen Hills what we concluded was strong evidence for past life. That evidence consisted of, number one, some little tiny fossil-like features that are similar to fossils known to occur on Earth. Number two, we found that there were crystals made of an iron oxide, which are also always associated with bacteria on Earth.
McKay and his team believe that the Allen Hills meteorite is proof that life existed on Mars. When they announced their discovery in 1997, most scientists were skeptical.
The discovery of fossils in the Martian meteorite was always problematical. They weren't really biological structures, they were just little round and little oval-shaped things. And people quickly realized that if you pick up any piece of rock or dirt and examine it at that scale, you often see little round and little oval-like structures that have nothing to do with biology.
But Spirit's discovery of silica on Mars has reopened the debate about Martian microbes. If extremophiles can be found in similar environments on Earth, then why not on Mars? Will Phoenix find the evidence that backs up McKay's belief that life existed on Mars? If it does, the implications will be profound.
You may think that if we find life on Mars and it's just microbes, who cares? Why is that important? But within those microbes could be the potential for all of the richness and complexity of life like we see on Earth. In the same sense that an acorn is an oak tree, a single organism on Mars could represent the potential for complex ecosystems for animals and plants and even human-like intelligence. Even if on Mars that seed didn't grow to its full potential, if the acorn didn't become an oak tree, it's still interesting because it tells us that on other worlds, on other stars, it would have fully developed. We're not alone.
It's an astonishing prospect, one that the Phoenix mission is poised to solve.
Well, when Phoenix lands down on Mars and sends back its first signal that it lands successfully, I will breathe a 5-year-long sigh of relief.
But before NASA's latest probe can answer tough questions about life and our place in the universe, it first faces its biggest challenge: descent and landing. NASA's latest mission to Mars will try to answer some fundamental questions about the red planet and the nature of life in the universe. When Phoenix begins searching ice for traces of life, it takes us closer to understanding our place in the solar system. Is life on Earth a quadrillion to one miracle? Or does it appear wherever and whenever the circumstances are right? Before it can answer these questions, Phoenix has to safely get to Mars. NASA's probe approaches the planet at 74,000 miles per hour.
All stations, Heliocom. At this point, we have a strong signal from Phoenix via Odyssey.
On May 25, 2008, at 7:46 p.m. Eastern Standard Time, the team at JPL begins slowing the spacecraft down for a soft landing on the planet's surface.
It loss of the X-band signal from the DSN does indicate an expected cruise stage separation.
This man is responsible for bringing its speed down from 74,000 to 5.5 miles an hour. He's Gentry Lee.
The risky part of the mission begins as we near Mars. When we hit the top of the atmosphere, the process of slowing down begins. And in that 6 to 7 minutes, we slow down from tens of thousands of miles an hour to single digits miles per hour so that we can land softly.
It's a process that involves 3 distinct phases. They're called EDL: entry, descent, and landing. Each is potentially deadly. Friction from the atmosphere slows the craft to about 750 miles per hour.
First, you have a heat shield, which takes this enormous potential energy and converts it into heat. That's 99% of the deceleration. Then when it's done, out pops a parachute, and it takes another 99% of the speed out.
The parachute's performance is crucial to the success of the mission. Up to this point, Phoenix's EDL is identical to any other Mars mission. But unlike the rovers before it, Phoenix has no airbags to cushion its landing. Instead, it uses 12 descent rockets clustered around the hull to slow down. In the final 34 seconds of descent, they fire rapid pulses, carefully timed to bring the lander down at 5.5 miles an hour. If Phoenix's engines fail, its terminal descent will have been just that. For controllers, this is one of many things that could have gone wrong.
And then, of course, will come the moment when it's too late to even ask any questions.
Standing by for possible flashing blackout.
Did the radar see the ground properly? Did the computer interpret the information properly? Did the pulsing engines do what they were supposed to do? I can't wait. Will somebody please tell me now?
On May 25th, 2008, at 7:53 p.m., Phoenix starts its descent.
Ground velocity 90 meters per second. Touchdown signal detected. Landing sequence initiated.
The landing is a success. For the team, this is the culmination of 5 years' hard work, and yet the mission is just beginning. These are the first images Phoenix sends back to Earth. The search for life on the red planet begins. Saturn, one of the most mysterious planets in our solar system. Now the Cassini-Huygens mission is exploring this enigmatic world and its moons. For the first time, it allows scientists to see what lies below Saturn's upper atmosphere and investigate the origin of its incredible rings. A probe touches down on the largest moon, Titan, to search for a world like our own and the possibility of life.
Five, 4, 3, 2, 1, and liftoff of the Cassini spacecraft.
4:43 a.m. October 15th, 1997. An 1,100-ton Titan 4B rocket launches from Cape Canaveral. It carries with it Cassini-Huygens. Its destination lies almost 900 million miles away at the awe-inspiring planet Saturn. A huge gas giant orbited by at least 60 moons. Saturn is the second largest planet in the solar system, over 750 times more massive than Earth. It's a gassy world without solid surface. The last mission to this mysterious planet launched over a quarter of a century ago. The Voyager spacecraft sent back these images, showing a planet shrouded in thick banded cloud. Onboard infrared cameras spot what looks like storm activity beneath the haze. Something big is brewing on Saturn.
The problem with Voyager missions is that they were flyby missions. They were one-time snapshots.
Voyager can't stop to investigate. Its flight plan is fixed. Scientists can only gather limited data. Voyager 1 also skims the atmosphere of Saturn's largest moon, Titan. Scientists are shocked at what it finds. Its instruments detect organic compounds in the atmosphere. These are similar to the compounds that provided the raw material for life on Earth 4 billion years ago.
In a way, Titan is a glimpse back in time to processes that may have been occurring on the early Earth that may have led to life.
But once again, Voyager 1 can't stop to investigate. It hurtles off at 39,000 miles per hour into the cold outer reaches of the solar system. The Voyager mission makes tantalizing discoveries, leaving scientists with more questions than answers. They are determined to return to the mysterious moon and take a closer look.
We want to understand our own origins. We want to understand why the Earth came to be the way it is and how life came to develop here.
Scientists believe by unlocking some of the secrets within Saturn and its moons, we could learn how our own world developed and how life began. Cassini is one of the most scientifically advanced spacecraft ever launched. It will explore Saturn's atmosphere using an array of high-tech cameras and sensors. Cassini carries with it a probe called Huygens. This will deploy to Titan, Saturn's largest moon. It will plunge through the thick atmosphere and land on its surface. But first, Cassini must make the long haul through 2 billion miles of space. The mission control team used the gravitational pull of our neighboring planets to slingshot the spacecraft around Venus, Earth, and Jupiter, giving it enough momentum to reach Saturn. After 7 years of flight, Saturn looms into view. Cassini captures this stunning image of the gas giant. But before it can get close enough to begin its detailed exploration, Cassini must pass through the rings. The rings are chaotic and dangerous. Made up of billions of particles of ice and rock, circling around the planet at high speed. Some chunks are as big as houses. The only way through is to navigate a gap between the rings. Dr. Jeff Kuzi is in mission control as Cassini approaches the gap.
The gap isn't something you would see with your eye. So it wasn't exactly like there was a huge, tight tolerance, a narrow, threading the needle kind of a thing.
Tension builds as the high-risk maneuver begins. Cassini fires its rocket engines to position itself and heads for the gap. Its antenna points away from Earth. Communication is temporarily lost. Dr. Larry Esposito waits for the signal to return. The sign that Cassini has made it through in one piece.
Everyone was holding their breath, waiting for the signal to come from the spacecraft to show that it had successfully passed through the ring plane.
Several hours later, they get the signal.
The Doppler has flattened out.
Cassini has made it through.
Once that happened, the silence ended, broke into cheers, applause. People hopped up, shook each other's hands. Some people hugged each other. It was a great moment of success after decades of planning.
For the first time, a spacecraft has entered orbit around a planet in the outer solar system. And for Dr. Tony Del Genio, it's in the perfect position to start exploring this gas giant.
The beauty of the Cassini mission is that for the first time, we get to go into orbit around a planet like Saturn, and for years observe it over and over again from different angles. And by putting that together over this long period of time, finally some of the secrets start to be revealed to us.
The first task is to explore what lies beneath Saturn's thick upper atmosphere. Cassini maneuvers towards the South Pole. There, its instruments reveal an unexpectedly familiar phenomenon. A monster hurricane-like vortex. This actual image clearly shows the storm and its scale.
This feature is more than 1,000 miles across, so many times the size of a real hurricane on Earth. And what you're seeing is a sequence of images showing the clouds rotating around the South Pole.
This is the first hurricane-like storm ever detected on any planet other than Earth. Like hurricanes on Earth, it has an eye circled by a gigantic column of cloud. But this one towers 45 miles high. Around it, winds rage at 350 miles an hour. Cassini's cameras zero in on the high-altitude clouds in the upper reaches of the eye wall. Temperatures here are minus 167 degrees Fahrenheit. The pictures capture what must be a flurry of ice crystals. Scientists are enthralled. Like Earth, Saturn has storms with swirling clouds, strong winds, and even snow.
It definitely snows on Saturn in the upper reaches of the storm systems that we see. I think we're pretty confident that there would be large ice crystals. When you got down much deeper than we can see to in the images, then we would expect actual liquid water rain to be falling out of the bases of those clouds.
On our planet, hurricanes are fueled by the ocean and ultimately the sun. Saturn is far too distant to draw the kind of solar power its monster storms need. So what drives them?
When you get into a gas giant atmosphere like Saturn, once you get a wind going, you can maintain it for a long period of time without a solid surface underneath it to dissipate it very quickly. But still, slowly over time, if you didn't somehow put energy into the system, the winds would still dissipate.
Now scientists investigate the theory that the energy for the storms comes from deep inside the planet. It's a theory they've never been able to prove. But at a laboratory in France, an extraordinary experiment is trying to verify its basic principles. Cassini captures these images, showing a monster storm on Saturn. A gigantic hurricane 2/3 the diameter of Earth rages at the planet's south pole. Winds encircle the central eye at over 350 miles an hour. Scientists want to know what fuels these storms. Saturn is too far from the sun for them to be driven by solar energy. The power source must lie elsewhere. Many scientists believe it comes from deep within the planet. At the Coriolis Laboratory in France, astrophysicist Peter Reed searches for evidence to support the theory. He is using an internal heat source to recreate Saturn's turbulent atmosphere.
The overall objective is to try to come up with an understanding of what processes actually drive the winds and organize them into banded structures and into these sets of alternating eastward and westward jet streams on Saturn and the other gas giants.
Inside this huge rotating tank is almost 40,000 gallons of fluid. This acts like Saturn's gases. A heater sits in the base of the tank to simulate a heat source deep inside Saturn. Suspended in the fluid are tiny light-sensitive particles.
So these particles act basically like clouds in Saturn's atmosphere, so they'll be carried around by the winds, and this will help us to actually trace out where the vortices and the jets are actually occurring.
Reed wants to see if currents and vortices develop in the same way they do on Saturn's surface. The tank spins to mimic the rotation of the planet. The tiny particles start to spread out and interact. Slowly, the particles begin to swirl and create vortices.
Okay, so we can see evidence of a jet structure, and then here we can see a very nice rotating structure, which is basically an anticyclonic vortex.
Compare these to Saturn's twisting patterns of clouds. The similarities are striking. Reed's experiments suggest that a heat source within Saturn could fuel the raging storms. But what lies in its center that could generate that much heat? The gas giant is approximately 75% hydrogen and 25% helium, with traces of water, methane, and ammonia. Scientists believe that, like Earth, Saturn has a hot core. Earth's internal energy comes from radioactive materials in the core and residual heat from its formation. But here on Saturn, scientists think heat is generated by highly pressurized gases. Deep down in Saturn's atmosphere, the pressure of the gas builds. Near the core, the pressure is several million times higher than on Earth's surface. It's so powerful that the hydrogen and helium gradually turn from gases into strange metallic liquids.
If you get deep enough, then the hydrogen and helium become so dense that they don't behave like a gas anymore. They behave more like an electrically conducting metal.
This liquid swirls around a rocky core that is roughly the size of Earth. But just as oil and water can't mix, the liquefied metallic elements can't hold together. The heavier helium separates and sinks through the hydrogen. Scientists believe this movement creates friction that generates heat. Cassini is looking for evidence supporting this theory by measuring the precise abundance of helium in the atmosphere. It's already amassed a vast amount of data. There's so much that it will take years to analyze. Scientists hope to find out for certain how Saturn can give out 3 times more heat into space than it receives from the Sun. Cassini is unveiling Saturn's turbulent activity in unprecedented detail. Now its main engines fire, and mission control steer the spacecraft outward to explore one of the greatest mysteries in the solar system: Saturn's chaotic rings. Saturn has the largest and most spectacular rings in the solar system. The Voyager missions first revealed their awesome scale more than 25 years ago. The Voyager spacecraft show that the rings are chaotic. They're made up of billions of chunks of ice and rock colliding into each other.
If you were to fly over the top of the rings very close so you could actually see them, you'd see something that would look a little bit like a flying boulder field. Small particles ranging between a fraction of an inch in size and maybe a couple of yards across.
The turbulent rings got scientists thinking. The particles orbiting Saturn resemble the disk of gas and dust that encircled our young sun 4.5 billion years ago. The particles started clumping together, growing larger and larger, until after millions of years, they eventually formed the planets in our solar system. Could the same process be occurring inside Saturn's rings? Is this a good analogy for how planets may grow? Cassini sends back these stunning, highly detailed images.
I was very excited to see these beautiful, beautiful images. We're going to learn a huge amount just from the first couple of images.
Cassini uses an ultraviolet imaging spectrograph to map out the ring's structure with remarkable clarity.
The spectacular detail that we saw was just an eye-opener, and we stood amazed to see the structure that was in the rings, much more than I had personally expected.
As the particles pass in front of distant stars, the UV spectrograph measures the amount of starlight shining through. Areas that contain a lot of particles block starlight and appear darker. Where there are fewer particles, more light passes through. Scientists interpret the darker regions as temporary clumps of ring particles. They are known as moonlets. Cassini captures them on film for the first time. They appear as bright lumps within the rings.
These big boulders may very well be nothing but an agglomeration of the smaller ones. And these agglomerations may come and go with time as they bump into each other. They may just fall apart and collapse, and then they may reform by their own gravity and stickiness on the surfaces.
Scientists are fascinated by the images. They think this process happened in the early solar system. 4.5 billion years ago, the planets grew from microscopic specks to the size they are today.
The interaction between the moonlets and the ring particles is exactly like the interactions between a planet and the dust that's collecting to make that planet grow.
Cassini's spectacular images offer new insight into the processes behind the formation of our own world and the entire solar system. But where did all the material that makes up the rings come from? In its infancy, the solar system was a violent place. Comets and asteroids regularly collided with young planets, creating massive explosions and leaving behind scars that we can still see today. This image, modeled from real data, shows Saturn's tiny moon, Mimas. This giant crater dents its surface, a scar from a gigantic impact. Mimas was lucky. It survived the impact. But scientists think that Saturn could have lost one of its other moons completely, shattered into billions of fragments.
Imagine an object coming in that's the mass of a small planet or a big comet coming in. There's a huge amount of energy there. It could actually rubbleize it pretty well.
Saturn's powerful gravity could have captured the fragments and over time compressed them into a flat plane around its equator. These strange rings may be the result of the solar system's most intense period of planetary bombardment. They may also unlock the secrets of the solar system's birth 4.5 billion years ago. Cassini's next stop provides scientists with another opportunity to step back in time, to a world like Earth before life evolved. This is the mysterious moon, Titan. Cassini has crossed over 2 billion miles of space to reach Saturn and its moons. It carries with it a secondary space probe called Huygens, designed to land on Titan, one of Saturn's 60 moons. Titan is massive. It weighs almost twice as much as Earth's moon. It's an object that's perplexed scientists for decades. In 1980, Voyager 1 sends back these intriguing images of a world shrouded in a thick orange atmosphere. Analysis reveals that this is mostly made up of nitrogen, just like Earth's. The spacecraft also detects water and traces of organic compounds like ethane and carbon dioxide. Compounds that could provide the raw materials for life. Titan's atmosphere appears to be remarkably similar to that of early Earth. Now Huygens returns to pick up where Voyager left off, to search for signs of life. Dr. Carolyn Porco was a young PhD student on the Voyager missions.
You can imagine that for those of us who had been involved with the Voyager mission 24 years earlier, that there's a tremendous amount of anticipation in returning to the Saturn system.
Cassini's sophisticated cameras alone can't fully penetrate Titan's thick atmosphere. What's on the surface beneath the thick haze?
Our first pictures of Titan were very mystifying. In fact, our images are painted on this globe, and it's very difficult, if you look in details, to see exactly what you're looking at.
Cassini's probe, Huygens, is designed to solve this mystery. The probe hits Titan's dense atmosphere at over 13,000 miles per hour. At first, its cameras only transmit these images of a thick yellow haze. But at around 30 miles up, Titan's surface comes into focus.
It's just very difficult to describe accurately what it was like to see the first images that they showed of the surface of Titan, because they were mind blowers.
These images show an extraordinary desert-like landscape with low hills and rolling plains. But mission engineer Dr. Ralph Lorenz worries where Huygens will touch down.
We had no idea what it was going to land on. We didn't even know if it would survive landing. It could have landed in a lake of liquid hydrocarbons. It could have landed on a solid sheet of ice or a sand dune.
To the relief of all, Huygens lands on level ground and survives. It's the first probe to touch down on another world in the outer solar system. Onboard cameras reveal an eerie alien landscape. Lorenz rigged the probe with an instrument to analyze the composition of Titan's surface.
One thing it did is it had an instrument called a penetrometer, which was rammed into the ground and told us how hard the surface was. The texture was like damp sand or even a soft clay, and there were indications that there might have been a pebble or a crust on top, and there was even the joke that the surface was made of creme brulee.
The penetrometer reveals Huygens has touched down on soft ground, but not just any ground. Its camera shows smooth, round rocks, similar to those found in a riverbed.
There were a lot of rounded pebbles around, and the way you get rounded pebbles is that they're tumbled in a stream. And so this area, which had river gullies, must have been rained on sometime in the past, and the rain washed down, tumbling these pebbles.
Huygens discovers signs of liquid on the moon's surface.
So right away, there was this unambiguous sign of a process that we knew how to interpret. So this was tremendously exciting. It said there had to be liquid something flowing on the surface of Titan.
But is the liquid water? Huygens' thermometer registers the surface temperature as 290 below zero. In this bitter climate, water would freeze as solid as rock. But if water didn't carve this riverbed, what did? As Huygens continues to probe from the ground, Cassini moves to the moon's uncharted North Pole. Its radar penetrates the smoggy atmosphere to reveal dark patches. These indicate something astounding. Lakes. Liquid may still flow on Titan's surface. But what liquid can withstand freezing temperatures? Cassini's visual and infrared mapping spectrometer picks up a dramatic cloud system. It's enormous, engulfing almost the entire North Pole. Scientists suspect these clouds could supply the liquid that appears to fill Titan's lakes. Cassini homes in on the clouds and finds they are made of methane. It seems that Titan's surface has been carved not by water, but by liquid methane.
We've counted up the volume of liquid in some of these lakes, and it's hundreds of times the amount of all the liquefied natural gas, all the oil on Earth.
The super cold temperatures on Titan allow methane to exist as a liquid. Any water on this moon is frozen solid. Surface conditions are not conducive to life. But Titan's atmosphere is another story. Scientists focus in on the tiny particles suspended in Titan's atmosphere, first discovered 25 years ago. They are a cocktail of organic molecules, the stuff of life. Molecules like these existed on Earth 4 billion years ago. If scientists can understand how they form on Titan, they can figure out how they developed into life on Earth. Cassini isolates the exact mix of molecules and transmits its findings back to mission control. Astrobiologist Dr. Chris McKay has been trying to recreate Titan's atmosphere in the lab, using the data from Voyager.
As soon as the Cassini results came in, we scrambled to change our experiments, to line them up with the new information. It was like working on a problem for a decade and then finally seeing a glimpse of the answer in the back of the book and realizing, aha, this is the way to go.
McKay now tries to use this formula to turn simple organic molecules like methane and nitrogen into the building blocks of life. In his lab, he simulates Titan's pressure, temperature, and nitrogen-rich environment.
Here is a tank of methane and nitrogen. This is the starting mixture for Titan's atmosphere. It flows through the apparatus into our reaction chamber. So now I'm going to turn on the energy source, and this flow of methane and nitrogen will experience the same kind of energy processes that are going on in Titan's upper atmosphere.
Then McKay uses electricity to simulate the sun's ultraviolet radiation.
We have Titan in a jar.
After a few hours, the simpler molecules turn into complex nitrogen-rich substances called tholins. These lab-made tholins are almost exact copies of those found on Titan. Understanding how they form gives us valuable insight into the origin of life on Earth.
One overall question in studying Titan and comparing it to the early Earth is the question of how unusual is the sort of chemistry that led to life on Earth? Is it very rare and it happened on Earth because of very unusual circumstances? Or is it commonplace organic chemistry that we can expect on any world that's like Earth or even like Titan? And if we find that there's a common theme, a common way in which this kind of process goes, maybe the steps that lead to life are commonplace, and therefore life is commonplace.
The Cassini mission to Titan reveals how life could emerge on other worlds. On the surface, Huygens' batteries die out. Its landing represents one of the great achievements in the history of space exploration. Huygens provided a spectacular view of Titan and returned over 750 images and over 3 hours of data. Cassini abandons Huygens on Titan and heads for another moon, which scientists believe could be its greatest conquest, Enceladus. Cassini continues exploring the Saturnian system. In its sights, the moon Enceladus. Covered in ice, Enceladus is one of the brightest objects in the solar system. Cassini's cameras capture these detailed images of this dazzling, frozen world. Its ancient, wrinkled surface is made up of fractured plains, craters, and folded mountains. But as it skims past, Cassini's magnetometer registers some kind of disturbance. This is the actual recording. The moon creates fluctuations in Saturn's immense magnetic field. But how? The magnetometer detects gas coming from the moon's surface. Experts suggest it must have some kind of partial atmosphere. Planetary scientist Professor Bob Brown thinks this is impossible.
They said, hey, you know, we're seeing evidence of a tenuous atmosphere around Enceladus. And many of us responded with skepticism because an object like this can't have an atmosphere.
Enceladus is just 300 miles across. It has too little gravity to hold on to an atmosphere for very long. But things are about to get stranger.
The magnetometer group told us the atmosphere around Enceladus seemed to be concentrated around the South Pole, which is even weirder. Atmospheres don't do that. They distribute themselves uniformly around an object.
The team is mystified. What could create a strange, localized atmosphere? Cassini moves closer. The spacecraft captures this stunning image. Giant geysers on the surface of the moon appear to throw out huge plumes of vapor. The unidentified gas blasts over 400 miles into space.
To see this image, okay, where we have a dozen to 2 dozen jets, narrow jets, just emerging from the South Pole, was, it's one of those things that a person who lives the kind of life I lead lives for. Okay, it was just one of those discoveries that, you're not going to make often in your lifetime.
Cassini's spectrograph analyzes the vapor of the jets. It contains water. This discovery is completely unexpected. Could liquid water exist on this frozen moon? Cassini is looking for liquid water on Enceladus. It zeroes in on an area of the moon covered with cracks.
But one of the things that was absolutely stunning about this is that when we got into these areas where these cracks are, they're clearly a lot warmer. It may very well be that the temperatures there are as high as 0 degrees C. It may very well be that they're high enough that liquid water is literally very, very close to the surface.
Cassini has found a hot spot, an area warm enough to support water in its liquid form.
That was just, mind-blowing. Like, what could be possibly producing this? It's one thing to find a body to be warm. It's another thing to find that it's only warm in one location.
Scientists are baffled. What generates these pockets of heat? Enceladus's orbit is elliptical. Its distance from Saturn varies over time. One theory is, as it passes close to Saturn, its crust flexes. Then as it moves away, it relaxes. Friction at the fault lines generates heat. Perhaps enough heat to melt ice within the faults.
Enceladus flexes its body, okay, and so that can produce friction enough to melt ice to create liquid water.
The prospect of liquid water on one of Saturn's moons demands further investigation. The first step is to determine the exact composition of the plumes. Mission Control fly Cassini just 30 miles above the moon's wrinkled surface, passing through the geyser's outer edge. Its instruments measure the composition. The results are completely unexpected. The plumes contain water vapor, nitrogen, and even simple organic molecules.
It doesn't take much of a jump at that point to make the association that if you have water, you have heat, and you have organic chemicals, you have the conditions that might actually produce primitive life.
Scientists now believe that Enceladus has conditions that can sustain life. Living organisms could survive around the warm faults that sit at its southern pole. The latest theories suggest that the faults in the terrain here may stretch down to a subterranean sea. This would be a dark world devoid of sunlight, but life may still have emerged here. On Earth, primitive organisms thrive in similar hostile and extreme environments. Scientists speculate that the same could be true of Enceladus.
There's the possibility of having something akin to those hydrothermal vents that we see at the bottom of the ocean. And we know there are living organisms there. There's chemistry that goes on there that living organisms can utilize to live.
It's a tantalizing possibility. If there are living things on Enceladus, the implications would be profound.
What could be a more important scientific discovery than to find out life has evolved separately in some other place? That changes the whole picture for human beings.
If we could demonstrate that the origin of life, Genesis, had occurred twice independently, then as far as I'm concerned, the spell is broken. We could safely infer life had occurred an astronomical number of times throughout the cosmos in its 13.7 billion year history. So this is why it is such a pressing question for us.
Cassini shows us that life may be possible on alien worlds. On April 15, 2008, more than 10 years after launch, NASA announces that the mission will be extended for a further 2 years. Parts of its tour will be dedicated to the exploration of Enceladus and Titan. Perhaps it will make the biggest discovery of them all: life on another world. 65 million years ago, a 1,000 billion ton asteroid smashes into the Earth, wiping out the dinosaurs. Massive impact events are likely to happen once every 75 million years. Today, scientists scan the skies for these giant killers. But an asteroid just 150 feet across could devastate a city the size of New York. Asteroids this size could hit any time. And right now, there is nothing we can do to stop them. It's a nightmare scenario. 1,000 billion tons of rock on a collision course with Earth, hurtling towards it at over 50,000 miles per hour. It hits with the force of 300 million nuclear weapons. Enough energy to wipe out every human being on the planet. This is no nightmare. It's real. 65 million years ago, a rock this size smashes into the Earth. And wipes dinosaurs from the face of the planet. It could be 10 million years before the next impact this big. But smaller asteroid impacts can also be devastating, and they happen far more often. Around 50,000 years ago, an asteroid slams into the Arizona desert, hurling 175 million tons of rock into the air. Meteor crater is nearly a mile wide and 570 feet deep. Amazingly, the Canyon Diablo asteroid that created it was only 130 feet in diameter, about the size of a small jet plane. There are more small asteroids like this in space than large ones, and they can hit the Earth as often as every few hundred years. One scientist at Northern Arizona University thinks Meteor Crater has a message. Professor Ted Bunch.
Events like this, smaller events, they could happen anytime.
And they're capable of massive destruction. The extreme heat of this blast tore through the desert sandstone.
This is coconino sandstone, and it's in pretty good shape. And there's a piece here. This is also coconino sandstone that is severely shocked. Probably temperatures exceeding maybe 3,000 degrees Fahrenheit. Huge amount of pressures, and you can see the difference. This used to be this.
Imagine the same thing happening today. What would a 130-foot wide object like this do to New York City?
If this meteorite had hit Manhattan yesterday, about 80% of the people would have had serious injury or died. All the boroughs of New York would have been affected, either by the heat, the shock wave, the seismic activity, crumbling of buildings, and collapse.
everything within a 5-mile radius would be obliterated. Asteroids have crashed into our planet ever since its formation. The key to their destructive powers lies in their mass and the speed of impact. As an asteroid hurtles towards Earth, it builds up huge amounts of kinetic energy, much like this speeding car. The faster the car goes, the greater the kinetic energy, even though the car's mass stays the same. When the speeding car hits a brick wall, it doesn't inertly stop. All the kinetic energy is converted into an explosive force. The crash generates heat, metal bends, plastic and glass shatter. An asteroid behaves exactly the same way when it impacts the Earth, only because it's traveling at 50,000 miles per hour, the explosion is far greater. Here in Arizona, evidence of the impact stretches 6 miles from the crater's edge. Pulverized rock particles called impactites shot across the landscape at deadly speeds.
We have impactites, all these little dark guys. Those are melt rocks. There's literally tens of thousands of them right in this particular area. These were ejected as far as 3 to 5 miles under very high velocities, 2 or 3 times the speed of a rifle bullet. But if you were an animal in this area and you had thousands of these particles coming at you, you'd be toast.
Impactites are a major clue to an asteroid strike and can reveal previously unknown impacts. Fossil hunters in Alaska uncover fragments of tusk from woolly mammoths. They are peppered with buckshot-like particles and date back 34,000 years to a time when the number of large mammals in the region inexplicably dropped. Have fossil hunters uncovered evidence of an undocumented asteroid impact? Dr. Richard Firestone searches for evidence.
We analyzed several of the particles from various tusks, and they had the unique signatures of meteorites. They were rich in iron and nickel, which is a critical component of most meteorites.
This is strong evidence that these woolly mammoths died from an asteroid impact. The force of blast was devastating.
We did an experiment with a shotgun to see what would happen if you shot a mammoth tusk, and they simply bounce off the outside. Nowhere near enough energy for that.
A shotgun fires at 600 miles an hour. Asteroid fragments travel over 30,000 times faster.
In order for the impact particles to penetrate the tusks as they did, they'd have to have been moving at tens of miles per second.
Firestone's mammoth died in an asteroid impact 34,000 years ago. The impactites embedded in the mammoth tusks prove that previously unknown asteroids have struck the Earth. And new evidence reveals that they didn't just kill mammoths. Humans died too. "13,000 years ago, North America is locked in an ice age. Large mammals like giant sloths and woolly mammoths roam the land. The nomadic Clovis people live alongside them. Then the fossil record stops. Many species of mega mammal abruptly disappear. What causes this sudden, mysterious disappearance? The Clovis culture also vanishes from the archaeological record. Is it starvation? Disease? No one knows for sure. Now a cave in northern Ohio may hold the answer. 30 feet underground, an archaeologist from the University of Cincinnati discovers evidence of an ancient catastrophe. Ken Tankersley and his team dig up a layer of burnt material in the soil. It dates to when the Clovis and the mammoths vanished. To archaeologists, this distinctive carbon-rich layer, called the black mat, indicates intense burning, a sure sign of a destructive event.
Beneath this layer, we have evidence of large mega-mammals. Above it, there's none whatsoever. This mat was deposited in a very quick and sudden event. Beneath it, you have evidence of Clovis people. Above it, you have absolutely none. The real mystery is what happened at this very time.
What catastrophe caused this black mat? Tankersley searches inside the black mat and uncovers the bone of a wild pig, known as a peccary. It tells a disturbing story.
This particular bone has not seen air in 13,000 years.
The bone shows signs of extreme burning.
We know this burning is not the result of cooking. These animals were larger than I am, and to take a human body and a natural fire, you have to burn the body for days. This type of burning clearly came from a very intense, very fast burning, a single event fire, if you will.
Did an asteroid cause this deadly blast of heat? If it did, there is a vital piece of the puzzle missing. There's no evidence of a crater. This leads to a disturbing possibility. Could an asteroid be big enough to destroy an entire culture, yet so small it leaves no trace? Around 50,000 years ago, a small 130-foot wide asteroid smashes into the desert of Arizona and creates Meteor Crater. An impact this size could wipe out a major city. But this isn't the last time Earth was hit by a small but deadly asteroid. We're realizing that Earth is far more vulnerable than we once imagined. And some devastating impacts have left almost no trace. Archaeologist Ken Tankersley has found a black mat, evidence of an extreme heat event in a layer of rock dating back 13,000 years. The same time that the Clovis culture, one of the earliest in North America, abruptly and mysteriously vanished. Is an asteroid responsible? New research at sites across the United States also uncovers the black mat layer of burnt material, all dating back to the same time. The chemical analysis is compelling, but Tankersley wants to be even more certain. He returns to the Sheridan Caves in Ohio to take further samples. At the University of Cincinnati, an electron microscope takes a close-up view. Tankersley magnifies the tiny sample 10,000 times. He spots compelling evidence of a devastating asteroid impact. Detonation diamonds.
What's kind of tantalizing here is the possibility that these are associated with a cosmic event, if you will. Detonation diamonds are the result of a strong impact from either a large meteorite, an asteroid, or a slice of comet.
Major asteroid impacts have shaped history more dramatically than ever imagined. It seems increasingly likely that an asteroid is the reason for the Clovis culture's disappearance 13,000 years ago.
In geological time, 13,000 years ago is yesterday. The implications for us living on the planet today, we always think it's not going to happen to us. The reality is when it's going to happen next.
No one has ever found a crater from this event. So the question is, how big was the asteroid that caused this catastrophe? Asteroids are mostly composed of rock and metal, debris left over from the formation of the solar system 4.5 billion years ago. Thousands of these objects orbit near the Earth, some as big as mountains, others smaller than a speck of dust. The size of the asteroid that may have ended the Clovis culture is a mystery. One scientist thinks he can find the answer. Professor Peter Schultz of Brown University starts with one vital piece of information. The Clovis culture ended during an ice age. 13,000 years ago, North America is partially covered in a layer of ice up to a mile thick, the Laurentide Glacier. So the question is, what happens when an asteroid slams into ice rather than land? Schultz suspects the asteroid would leave a crater in the ice, a crater that might eventually melt, hiding all evidence of the impact.
The fact is, ice was there, and there's no reason why an impact couldn't hit there as well as any other place.
Schultz tests his theory in the vertical gun range at NASA Ames Research Center outside San Francisco. The vertical gun is unique. It can fire projectiles at 13,000 miles per hour, equivalent to the speed of a real asteroid. Schultz must find the exact ratio of asteroid size to ice thickness to cause a devastating explosion, but leave no crater. He uses a tiny glass bead in place of an asteroid and a half-inch sheet of ice for a mile-thick glacier. The experiment will tell Schultz how much damage a half-mile wide asteroid would cause.
We got about 3/4 of an inch of sand in there. We're going to be firing a projectile about 1/4 inch across, but the question is whether or not it's going to penetrate all the way through.
An asteroid colliding with Earth smashes into the atmosphere. Friction superheats it as it plummets through the air. Schultz simulates Earth's atmosphere by filling the chamber with argon gas. The gun will fire the projectile at almost 4 miles per second, the equivalent speed of most asteroids.
Every time you do an experiment, you learn something brand new. I love surprises, and invariably we have a surprise.
Could an asteroid be small enough to leave no crater, but big enough to devastate large parts of North America? It's a pressing question. The solar system is full of smaller asteroids. During the last ice age 13,000 years ago, an asteroid may have incinerated parts of North America, but left no crater. Scientists are trying to find out how an asteroid could be big enough to wipe out an entire culture and yet leave no imprint. Peter Schultz uses the vertical gun range to test what happens when a half-mile wide asteroid hits a mile-thick sheet of ice.
Oh! Pow! Oh my gosh! That's gotta hurt. Did you see that? Look at that stuff. Man, that hurt.
A glass bead enters the chamber at 13,000 miles per hour. When it hits the gas simulating our atmosphere, it burns and then explodes. A fireball smashes across the ice.
This is when you say, oh crap. It's coming for you. You can't even hear it because it's going faster than the speed of sound.
The experiment shows that a half-mile wide asteroid hitting a mile-thick ice sheet would have catastrophic consequences.
Oh wow, there's no crater. You don't even know that it happened. Let me go ahead and take some pieces out, okay? Here's where one big mass hit. You see the little pit in there. If the ice hadn't been here, we would have formed a crater about that big. The ice acted like a flak jacket. You know, once this goes away, once the water goes away, you can't tell that anything was here. That's remarkable.
The after effects of the impact would have been felt as far away as Europe. But the asteroid itself leaves no crater.
All you need is an object about a half-mile impacting into that. It might have formed a crater 20 miles across, but when the ice disappeared, melted, went away, you might completely remove the evidence. It's kind of like a perfect cosmic crime.
The asteroid that may have ended the Clovis culture could have been just half a mile in diameter. An estimated 1,000 asteroids of around this size hover near to Earth at this very moment. Scientists decide to look at other more recent impacts in order to reevaluate their size. One of the most famous and powerful recent asteroid impacts is known as the Tunguska event. June 30th, 1908, an asteroid explodes over Tunguska, Siberia with the force of 1,000 atom bombs. Tunguska is so remote that it takes 19 years for scientists to mount an expedition to examine it. The team brings survey equipment to record the devastation. The blast tore 60 million trees out of the ground. 800 square miles of Siberia, an area 1.5 times the size of Oklahoma City, are flattened and scorched. There is no crater. The asteroid exploded before it hit the ground. The size of the asteroid remains a mystery for almost 20 years. Then in the 1950s and 60s, impact specialists attempt to simulate the strike using data from nuclear tests. Some scientists estimate the Tunguska asteroid was up to 600 feet across. That estimate has been reduced to around 200 feet. In 2007, Dr. Mark Boslow reanalyzes the data using a supercomputer. He thinks the asteroid is much smaller.
Most of us had been thinking that it was an asteroid, came streaking in, it got down to about 5 miles above the surface and exploded with an energy of between 10 and 20 megatons. So we knew roughly what the wind speeds and what the thermal effects would be on the ground for an explosion at that height and that magnitude. And what was observed at Tunguska was consistent with that.
But this theory assumes a nuclear weapon and an asteroid impact in the same way. A nuclear weapon explodes from a single static point. But an asteroid is different. It's moving fast. So when it explodes, the energy it releases keeps moving, causing even more destruction.
When it explodes, it vaporizes, it begins to expand. It's very much like a nuclear explosion, except it's got a lot of mass and it just keeps on moving.
So the explosion over Tunguska spread out across the landscape.
We realized that even though it explodes at this high altitude, that explosion continues downward. All that hot rock, all that vaporized asteroid material continues downward, and finally it slows down and finally stops a few miles above the surface. The blue color here represents the shock wave, that blast wave that carries mechanical energy down. So that's very high wind speeds, hurricane force wind speeds. So when that hits the ground and sweeps across the ground, that's blowing trees down.
The old model assumed a stationary explosion. That meant a 200-foot asteroid. The model was probably wrong. A moving object could be small and still cause that much devastation.
The Tunguska event could have been caused by an asteroid as small as 100 feet in diameter.
Boslow's findings sent shockwaves through the scientific community.
There are many more smaller asteroids in Earth-crossing orbits than there are larger asteroids. Therefore, if Tunguska was from a smaller asteroid, a Tunguska-like event is more frequent than we had previously thought.
Scientists once thought an asteroid around 600 foot wide caused the obliteration of Tunguska. A rock that big hits Earth once every few thousand years. Now they've downgraded the size of the Tunguska asteroid to just 100 foot across. These hit on average every few hundred years, and the last one we know of was in 1908.
The most likely scenario for a big destructive impact event is from a Tunguska-sized object.
It's a game of chance. Another Tunguska-sized asteroid might not strike for another 100 years, or it might strike tomorrow. Luckily, the Tunguska asteroid hit in an unpopulated area. In today's world, we might not be so fortunate. The question is, what can we do to protect ourselves from asteroids, big or small? In 1998, the US Congress instructs NASA to take action. It sets up the SpaceGuard Survey to identify and track any near-Earth asteroids that pose a threat to our planet. The first step is to identify the asteroids at least 3,000 feet across, the ones big enough to cause massive destruction if they ever hit Earth. So far, 1,100 asteroids this size have been located. The Catalina Stewart Observatory at the University of Arizona is part of this SpaceGuard network. Asteroid hunter Ed Bayshore and his team comb the skies for these giant asteroids.
Essentially what we need to do is we need to image an area on the sky 4 times over the course of about 40 minutes.
The computer takes 4 telescope images of the same patch of night sky. The stars stay still. But near Earth objects, the asteroids, move through frame.
So for instance, here's the first image of a field that we just observed. There's the second image, there's the third, and there's the fourth. When we start it blinking, we can see that we have an object right here in the field. As it turns out, that is probably an NEO by the way it's moving.
But what about the smaller asteroids? The ones we think wiped out the Clovis culture or exploded over Tunguska? Right now, Bayshore doesn't search for them at all.
There's many more objects that are smaller. And just because they're smaller doesn't make them not dangerous. In fact, we think the objects around 300 feet in diameter and larger, which are much more numerous, may actually represent a considerable threat.
Now space scientists are determined to track these smaller asteroids. Among them is a man who is no stranger to the hazards of outer space, former Apollo test pilot Rusty Schweikert.
Now, it's very important that we start looking for these smaller ones because they hit with much higher frequency. From 100 to 150 feet in diameter and larger, we can start having serious effects on the ground. They are huge in terms of natural disasters.
The smaller the asteroid, the harder they are to find. They move at around 50,000 miles per hour in orbits that are extremely hard to track.
Because we've only been looking for the biggest ones up until this time, our telescopes really aren't adequate to give us the information, the early warning that we need on the smaller objects.
Tracking small asteroids requires specialized telescopes. These are still years away from completion. But occasionally, astronomers get lucky. In 2004, they pick up a moving object in the sky. Closer inspection reveals it's an asteroid, and it's 900 foot across. Researchers name it Apophis, after the Egyptian god of evil and destruction. It is big enough to destroy an area almost the size of Texas, and it is coming our way. In 2004, at the Kitt Peak Observatory, Arizona, scientists spot a new and relatively small asteroid. It looks like it is on a collision course with Earth. It is called Apophis, and it's 900 feet across. Around 10 times the size of the asteroid that created Meteor Crater in Arizona. At the Massachusetts Institute of Technology, Dr. Richard Binzel tracks its trajectory.
An impact the size of Apophis in terms of the immediate damage would be regional, roughly the size of France in terms of its immediate catastrophic effects.
Based on initial observations, researchers believe it has a relatively high chance of hitting Earth in 2029. The asteroid poses a real threat. Binzel needs to discover what Apophis is made of. He studies the asteroid via a remote link to a telescope in the Mauna Kea Observatory, Hawaii.
The instrument we're using is a spectrometer. The different minerals that are present in asteroids have very critical absorption bands, or very fingerprints, if you will, in these wavelengths of light that let us distinguish between different kinds of compositions, different kinds of minerals.
No two asteroids are the same. Most are solid, but some are loose piles of rubble. The majority are made of rock, but some are composed of metals and other materials. Apophis turns out to be mostly made of chondrite, a type of rock.
We think that Apophis is like this type of meteorite. It's an LL chondrite meteorite. And the beauty is that we can measure the properties of this meteorite in the laboratory. And if we scale this meteorite up to the size of Apophis, which we think is about 900 feet across, the mass of Apophis is about 20 million tons. The energy that it would have if it hit the Earth is about 375 megatons, the kind of energy we usually talk about with nuclear arsenals. And that's more than 20,000 times the energy of the blast at Hiroshima.
With the asteroid's speed and orbit mapped, researchers can predict its trajectory more accurately. New data suggests that the 900-foot asteroid is headed this way in 2029. It will miss Earth by just 18,000 miles. A near miss in astronomical terms. But if Apophis had been on a collision course, what could we have done? The most obvious solution is a nuclear bomb. The theory is that a blast could shatter it into pieces. But this approach is risky. The blast fragments could continue on a collision course with Earth. And to make matters worse, they are now radioactive. Instead of eliminating the risk, a nuclear explosion could increase it. Earth could get hit by a cosmic shotgun blast, resulting in even more widespread devastation. One scientist alarmed by this scenario is Dr. Massimiliano Vasile of the University of Glasgow in Scotland.
What could happen is that the shock wave due to the explosion of the outer crust fragment the asteroid. So it might be that basically we have not just one asteroid on the collision course with the Earth, but we have 2 or 3 asteroids.
Scientists are racing to find a better solution. They have suggested attaching rocket engines to push the asteroid off course, or even solar sails to pull it into a different orbit. These are possibilities, but they sound like the stuff of science fiction. Researchers are putting their weight behind a more feasible solution: knock the asteroid off its collision course. The project's code name, Don Quixote. At the heart of the team is space mission analyst Chris Saunders from Kinetic Labs, England.
We are simply going to try and hit the asteroid and deflect it out of the way.
The theory is that a powerful strike delivered by a probe could knock the asteroid off its course, like a game of cosmic pool. Don Quixote is a 2-stage spacecraft made up of the impactor and the orbiter. The ion engine powers the orbiter to its target. Solar panels create an electric field, which ionizes an ultralight fuel load of xenon gas, ejecting ions from the engine to thrust the craft towards the asteroid at up to 200,000 miles per hour. The aim is to catch the asteroid as far away from Earth as possible, so that even a tiny push will move it off course. The observer locks into orbit around the asteroid and guides the impactor to an inch-accurate surgical strike.
It would move the asteroid's orbit by maybe 50 to 100 meters. That would be enough for the asteroid to safely drift past the Earth.
If astronomers locate an incoming asteroid early enough, Don Quixote might be able to deflect it. But it's untested technology with a huge margin of error. Most scientists agree a backup plan is essential. To defend Earth from an asteroid strike, scientists have an ingenious and radical approach. Use an intense ray of light to vaporize part of the asteroid's surface, creating a jet of gas that will move it off course. It's a good theory, but right now the only place Massimiliano Vasile can test it is in the lab. He uses the Industrial Laser Lab at Glasgow University to gauge how much light energy it takes to move an asteroid.
We can see the effect of the light of the laser that basically was burning the rock. This is what we expect would happen in space when we focus the light of the sun on the surface of the asteroid. The effect that I obtain is exactly as if I had a rocket engine attached to the asteroid, but the difference is that the engine is the asteroid itself. This is in fact one of the most effective ways of deflecting the asteroid.
But shifting a full-scale asteroid would take a lot more light than an industrial laser. Luckily, in space, we have a huge power source available, the sun. Vasile proposes using mirrors to focus sunlight on the asteroid, enough to vaporize its surface, just like the laser. But moving a 1,000-foot asteroid requires a mirror so large that no rocket is big enough to carry it into space. The solution? Use several small ones at once.
We propose to have a swarm of satellites, each one carrying a smaller mirror.
The mirrors would be around 60 feet across and precisely shaped to concentrate the solar energy, creating that vital jet of vaporized rock. Whatever system scientists end up using, the key is to catch the asteroid as early as possible. Astronaut Rusty Schweikert thinks it's vital to be prepared.
Even you and I driving our car, you and I typically have one chance in 10,000 that we're going to have an accident tomorrow if we're driving tomorrow. And because of that, we buy insurance. We're driving around the solar system on our planet totally uninsured. Why?
Someday, humanity will likely face another asteroid, like the one that exploded over Tunguska, or wiped out the Clovis culture. An asteroid just 150 feet across could kill tens of thousands of people, and we still don't know enough about them. The dangers and our lack of knowledge became all too apparent in September 2007. Caracas, Peru. Local people noticed strange lights in the sky, followed by a huge explosion. Villagers stumble on a 50-foot wide crater in the highlands. Locals claim it is caused by an asteroid, but not all scientists are convinced. Impact specialist Peter Schultz thinks it's a hoax.
My immediate reaction was, are you kidding me? This has really happened? It can't really be something that actually got through the atmosphere. This is science fiction. And the first pictures that came out, it looked like a B movie with this crater where Superman was going to walk out.
Schultz is disturbed by the size of the crater. It's tiny. An asteroid that small should never have made it through the Earth's atmosphere. It should have burnt up on entry. September 2007, a fireball blazes through the skies of the Peruvian highlands. It crashes to Earth near the village of Carancas in southern Peru, leaving a crater 50 feet in diameter. Eyewitnesses are mystified. At first, they think they're under attack.
We looked up at the sky and saw a smoky trail. First we thought it was a military plane. Then we saw that the object was approaching the ground, heading south. The workers said to me, I think that plane is out of control. We were really scared. Even animals are running away due to the loud noise.
One explanation is an asteroid strike. But how did an asteroid so small survive entry into the atmosphere? It should have disintegrated before impact. Peter Schultz, one of the world's leading impact specialists, travels to the site to investigate.
I heard the stories in the media, I saw the pictures, and I thought, oh my gosh, I've got to go there.
The impact has blasted chunks of Earth into the air, damaging a building 150 feet away.
Wow. Oh, jeez. Oh. Oh, my gosh. Wow.
Whatever caused this crater was powerful enough to blast 100 tons of soil across the landscape.
This is clearly the pre-existing soil. And everything was just simply turned upside down over this.
This has all the hallmarks of an asteroid crater, but Schultz is skeptical. He needs to find a fragment to prove it. He exploits a common characteristic of this kind of asteroid, its magnetism. The metallic fragment and the shape of the crater convinced Schultz that this was an asteroid strike. But how big was this asteroid? Eyewitnesses tell Schultz the angle of impact. Now if he can discover the speed, he should be able to discover the size. At the NASA Ames Research Center, Schultz examines the fragment of asteroid under a powerful microscope. It reveals the true story behind the impact.
The fragments were deformed. There were fractures, and they were in a pattern that happens at around 3 to 4 miles per second, almost 5 times a speeding bullet.
Schultz now has all the clues he needs to figure out the size of the asteroid.
From those pieces of information, the angle and the speed, we can determine how big it was. And it's probably somewhere between 3 feet and 6 feet.
It's an extraordinary discovery. Up until this moment, scientists believed rocky asteroids this small burned up before they hit the ground.
Here we have a puny thing, only about 3 to 6 feet across, that somehow made it to the surface. This shouldn't have happened. This just shouldn't have gotten through the atmosphere. In this case, it made it through. It not only made it through, but it hit hard.
How it got through exactly is still a mystery, but the fact that it did is alarming. If a tiny asteroid like the one that hit Caracas strikes a crowded city, it could potentially kill dozens, if not hundreds of people.
Will it kill people? Yeah. The clock is ticking. It's coming.
This is not one of those giant things. This is the type of thing that if it happened in New York, it would have caused some serious damage. It probably would have gone right through the ceiling of a tall building and gone through about 4 or 5 floors before it rested.
In Peru, we were thrown a hypervelocity curveball.
Rusty Schweikert believes that now is the time to take the threat from smaller asteroids seriously.
A hurricane, we can't prevent. A flood, we can maybe do some things to prevent. We can certainly mitigate against these things. But preventing is an unusual opportunity in a natural disaster. We can prevent this from happening. If we do our work with near-Earth objects, we can prevent asteroid impacts from ever happening.
There is little doubt that an asteroid will someday threaten the Earth. The question is, will we be prepared to deal with it in the not-too-distant future?